Okay, dear students, now we'll study about the relationship between load intensity, shear force and bending moment in a beam. Now let us consider a beam AB subjected to a general loading as shown in figure. In this figure, the free body diagram of an elemental length delta x at a distance x from the left support is shown. You consider an elemental length delta x at a distance small x from the left support. So this is drawn here. Now here you can see the positive senses of all the forces and moments. Right downwards is positive and right anti-clockwise is positive bending moment. Right downwards force is positive shear force and right anti-clockwise moment is positive bending moment. So this is the enlarged view of this elemental length. So what are the forces acting here? Let us take F be the shear force acting on the left portion of this, force acting on the left portion of this elemental length. So after the elemental distance delta x, let the shear force increases by delta F. So let us take this equal to F plus delta F. Let M be the moment on this left portion of the section. Let W per meter length is the load intensity for an elemental length delta x. Since it is very small length, we can take this load intensity to be a constant. Intensity of loading for this elemental length to be a constant. Let the moment acting on the left portion of this section be, this elemental right portion of this elemental length be m plus delta m. Okay. So first we'll consider the vertical equilibrium of forces. Let us consider the vertical equilibrium of forces. So while considering the vertical equilibrium of forces, what are the forces acting? What are the forces acting on this elemental length? So let us take the sign convention as, let the sign convention be like this. You have studied in first year the sign convention like this. Write all the downward forces as negative and all the upward forces as positive. Let us take the same convention. And you have taken anti-clockwise moment as positive and clockwise moment as negative. So let us take the same sign convention. So what are the forces acting downwards? F is acting downwards. You have taken it as negative. So minus F. This F plus delta F is acting upwards. So plus F plus delta F. This load is also acting downwards for a distance of delta x. So the total load is W into delta x. Load intensity is W per meter length. So for delta x length it is W into delta x acting downwards. So it is, we can take it as negative. So when you consider the vertical equilibrium, the forces acting are minus F minus W into delta x plus F plus delta F. No other vertical force is acting. So this can be equated to 0 when you take the equilibrium condition sigma V equal to 0. We are taking the equilibrium condition sigma V equal to 0. So you will get this F and minus F cancels. So the remaining is delta F minus W into delta x equal to 0. Or you can write W equal to delta F by delta x, where W is the load intensity per unit length. So in the limiting case, as delta x tends to 0, we can write dF by dx equal to 0. That is the first derivative of shear force is load. First derivative of shear force is load. Okay. Now let us consider the moment equilibrium. We are taking the moment equilibrium condition. Sigma m about the right phase is equal to, right phase of the elemental length is equated to 0. So you consider what are the moments acting. Now let us take the moment of all these forces about the right phase of this elemental length delta x. So taking moment equilibrium of the element about the right phase of the element. What are the moments acting? M plus delta m. It is anti-clockwise. We have taken anti-clockwise as positive. So m plus delta m Then this m is clockwise, so it is negative minus m. Then what is the moment of this F about the right of the section? It is acting downwards. So moment of this force about the right section, this is producing an anti-clockwise moment. Anti-clockwise is positive. So plus F into delta x. Now what is the moment of this load about this right face? W into delta x is the total load, and it will be acting at the center of this span. So the momentum will be delta x by 2. So W into delta x by 2. This should be equal to 0. Sigma m about the right face equal to 0. So now let us neglect the small quantities of higher order. This delta x into delta x becomes delta x square, which is a smaller, even smaller quantity than delta x. So we can neglect this quantity. This m and minus m cancels. So the remaining part of the equation is delta m plus f into delta x equal to 0. So we can write delta m by delta x equal to minus f. So what is the limiting case when x tends to 0? We can write dm by dx equal to minus f. That is the first derivative of bending moment is shear force. Okay. So the first derivative of shear force is load, and the first derivative of bending moment is shear force. Okay. Students, now we'll see about shear force and bending moment diagrams. Now what is a shear force diagram? Shear force diagram is a graphical representation of the distribution of shear force along the length of the beam. Okay, it is a graphical representation. It is similar to a graph, and the graph is drawn on a baseline which represents the centroidal axis of the beam. It is usually taken as the x-axis. The x-axis represents the centroidal axis of the beam. Now positive values of the shear force. Now we have seen shear force may have positive and negative values. If you are taking a section line, all the forces acting downwards to the right of the section is taken as positive. So positive values of shear force are plotted above the baseline and negative values below the baseline. For example, by adopting the positive sign convention is shear force diagram for a typical simply supported beam is shown like this. So if you have a beam like this, this is subjected to an eccentric loading capital W at a distance small a from the left support. Let L be the length of this beam. Its support reactions will be RA is WB by L and RB WA by L. So what is the sign convention? All the forces to the right of the section downwards is positive. So our sign convention is right downwards positive. So you consider this WA by L reaction is acting upwards. So right upwards is negative. So you have to plot the shear force value downwards, that is below the baseline. So this value is WA by L. It remains constant up to this loaded point. So this is constant, and at this point this W is acting downwards. So this WA by L is negative and this W is positive. So W minus WA by L, that you will get WB by L. It is, you are getting it as positive. So you have to draw it above the baseline. Now this will continue, this value WB by L remains constant up to this support, and this value of support reaction will be equal to the shear force at the supports. Okay, the value of support reaction will be equal to the shear force values at the supports. So we have to plot the positive values of shear force above the baseline and negative values of the shear force below the baseline. baseline represents the centroidal axis of the beam. It is usually taken as the x-axis, and you have to represent the shear force along the y-axis, and the x values, the distance values along the baseline or the x-axis. Okay, so we are plotting the shear force values in the y-axis and the distance values along the length of the beam on the x-axis. So what are the things we have to mark? We have to mark the salient points, like the points where the values are maximum or minimum, and the points where the nature of variation changes. So here you can see the shear force diagram varies from negative to positive at this point. And we have to mark the nature of variation between the salient points. Okay, so these are the points you have to mark in a shear force diagram, and you have to write at the bottom of this diagram SFD, and you have to mark what are the values at this salient points. Okay, now we'll see what is bending moment diagram. Bending moment diagram is a graphical representation of the distribution of bending moment along the length of the beam. Okay, similar to shear force diagram is the graphical representation of shear force. Bending moment diagram is a graphical representation of bending moment along the length of the beam. The graph is drawn on a baseline which represents the centroidal axis of the beam. It is usually the x-axis. So positive values of bending moment can be plotted above the baseline, that is the x-axis. So the x-coordinate shows the position along the centroidal axis of the beam, and y-coordinate shows the value of bending moment along the length of the beam. So usually we can plot the positive values above the baseline, but however the convention generally adopted is to draw the bending moment diagram consistently on the tension side of the member. So what is the meaning of tension side? When a simply supported beam like this is loaded, you can see that the beam will bend like this. So there will be tension at the bottom of the beam and compression at the top of the beam on a simply supported beam. So usually we can draw the positive values above the baseline like this, but in convention we are drawing the bending moment diagram on the tension side. So we are taking drawing the positive values on the tension side. So tension at the bottom. So here we are drawing the bending moment diagram on the tension side. Another example, you consider this frame. This has a vertical column and a horizontal beam subjected to a load. So this is a cantilever portion fixed at one end and free at the other end. So when it is subjected to a load, this will bend like this, and the top portion has tension. So we will draw the bending moment diagram on the tension side. Okay, so actually bending moment diagram, we will draw it on the tension side of the beam. So what is shear force diagram? It is a diagram in which the ordinate represents the shear force and the abscissa represents the position of the section. Is called a shear force diagram. Bending moment diagram is a diagram in which the ordinate represents the bending moment and the abscissa represents the position of the section. Now here we have to show the point of contraflexion in bending moment, that is the point where the bending moment changes its signs. So we have to show the salient points like the maximum value, minimum value, variation, and also the point where the bending moment changes the sign, that is the